The mole is a group of 6.022 times 10 to the 23 items. And that's a really large number. I'm going to expand that. 6.022. So I've done 1, 2, 3, just 20 to go. So a mole is a really large grouping number, but it's an important grouping number. And it was designed so that we could use masses on the periodic table in two ways, items. And here I have the grouping number to only 1, 2, 3, 4 sig figs. It is known, the rest of these are just placeholders. It is known to more digits. Okay, so which group has more, a dozen elephants or a dozen mice? And the answer is, well, a dozen is a dozen, so they have the same number because a dozen is a group. There are other grouping words. For example, pair means 2, and decade means 10. Dozen means 12. Ream means 500. A ream of paper is 500 sheets of paper. And a mole is 6.022 times 10 to the 23rd. It's just a large group. So which group weighs more? And the answer would be the elephants. Why? Well, 12 elephants and 12 mice is 12 and 12, but elephants just have a lot more mass. And so it's going to weigh more, a dozen elephants. And the same thing is true for the elements. If I was to consider two elements, maybe I'm looking at helium on the periodic table and something larger, maybe xenon. I can have a mole of atoms, which is 6.022 times 10 to the 23 atoms. But a mole of xenon is going to have a lot more mass. Why? Because every xenon atom has more mass. A typical helium might be helium-4. So here I'm picking one isotope of helium. Helium-4 would have 2 protons, 2 neutrons, and 2 electrons. And neutrons and protons have a mass of about 1 AMU, and electrons have a mass that's much less than that, but it adds up to 4.003. Okay, now that was an isotope. I'm going to get rid of my isotope and talk about your average helium. So weighted average of all the isotopes, we have 4.003 AMU per atom. And that's just based on the 6 pieces that would comprise your most common isotope of helium. And then we look at xenon. Xenon has a weighted average, so that the collection has the mass that would be, if there is no xenon with this mass, but typically about 131 AMU per atom. So it's just a bigger thing because it has more protons and more neutrons, and electrons don't count for much, but it has more electrons. Okay, so this grouping number, we can look at different collections. So each of these collections is a mole of whatever is specified. So in this case, we have mercury 2 oxide. Mercury 2 means mercury plus 2. Oxide, based on the periodic table, has a charge of -2. So it's an ionic compound. I put those together and I get HgO is the formula for mercury 2 oxide. And if I wanted to know how many are, well, the answer here is everything is a mole. So these collections are all a mole, which is equal to 6.022 times 10 to the 23. And in this case, we would say formula units. Why am I saying formula units? Because I'm talking about the unit, HgO, that represents the formula, that represents the crystalline structure, the large, long, three-dimensional repeating pattern. And so I use the word formula unit, or sometimes they abbreviate FU, excuse me, when I'm talking about things that are ionic. Okay, the next one is sucrose. And sucrose is sugar. There's a lot of sugars, but this particular sugar would have a formula of C12H22O11. So this is a molecular species because carbon, hydrogen, and oxygen are all nonmetals. And so they're sticking together for reasons that have to do with sharing electrons. So in this case, I could say that a mole equals 6.022 times 10 to the 23 molecules. Here we have sulfur. Sulfur is a molecular element. Sulfur is one of those allotropes that you just have to memorize, a polyatomic element, but there's 8 sulfurs per unit. And so that's a molecule. A mole of that is that many molecules. Here we have something called a pentahydrate, but I'm not going to worry about those for Chem A. You will see those in Chem 1A. Sodium chloride is a salt. Sodium is a +1 ion because it's an alkali metal. Alkali metals lose 1 electron to become stable, like neon. And then chloride is a way that chlorine can become stable. And chloride is isoelectronic with argon. I'm saying a lot of words, assuming that you have absorbed everything that I've said throughout all the Zooms up to this point. So if you have questions, that is totally fine. And please stop me and ask them. Okay, and then the last one here is atoms of copper, because copper is a metal. So the items could be formula units, like mercury 2 oxide and sodium chloride are the formula that represent the smallest whole number unit for ionic compounds, or molecules like sucrose and other things, water, carbon dioxide, or it could be for atoms. And there's one more thing that we often refer to in how many mole is that, and that is ions. So we're talking about here the smallest unit, and the smallest unit includes those 3 plus ions. Okay, so the particles that can be grouped could be atoms, and the atoms could be metals, or the atoms could be nonmetals, or the atoms could be metalloids. We could be talking about ions, like mercury 2, or oxide, sodium ion, or chloride ion. We could be talking about molecules, like sucrose, or carbon dioxide, or water. Or we could be talking about formula units, which is a fancy way of saying the formula for an ionic compound. And so to be ionic, it's anything that has made of ions. So it could be metal plus nonmetal. Like sodium, metal loses electrons and chloride gains electrons and they stick together. It could be something that's, so typically when we look for something ionic and refer to a formula unit, we're looking on the left and we see a metal. But there is one ion that behaves as an ion and makes ionic compounds, and that's ammonium. So we have to watch out for that, because if we see something starting with ammonium, it is also ionic. Okay, are there any questions on what the particles could be? All righty. So to get from particles to group, we're going to use this number, and this number is called an A, and the A stands for Avogadro, who is the scientist that is credited with coming up with this grouping. So we call Na Avogadro's number, and that is equal to 6.022 times 10 to the 23 particles. So to get from particles to a group, we use Avogadro's number. Just like to get from particles to a dozen, we use the number 12, but we haven't given anybody credit for that name, that number, that grouping. Okay, so I'm gonna write to get from atoms to a mole, or to get from a mole to atoms, I use Avogadro's number. To get from molecules, like carbon dioxide, something that's covalently bound to a mole, or back, I use Avogadro's number. Sometimes we're going to go from formula units if it's ionic. And sometimes we're going to consider ions, the pieces that make up the formula units. But in each case, to get to the group, we're going to use this number. And so it's important that you know how to use it and that you have a calculator that you've learned how to use, because you don't want to type in all those zeros. Okay, so how many silver atoms, in 0.33 moles? And we abbreviate mole, this is crazy, by just dropping the E. And so if I want to go from moles to atoms, I'm going to multiply by Avogadro's number.
Really quick,
Yeah.
from silver, you're using what number from the periodic table from silver?
I don't need a number yet. It's
Okay.
number 47.
Okay.
But I don't need it yet because I don't need a periodic table if I'm working with Avogadro's number. We will need it in a minute though.
Okay.
Okay, so right here, I've taken the relationship, which is 1 mole of silver is equal to 6.022 times 10 to the 23 atoms of silver. I've made it into a conversion factor, and I put the moles on the bottom because I need the moles of silver to cancel. So I end up with silver atoms so that I can answer the question. Okay, so how to put this in my calculator. For this kind of calculator, I'm going to type in 6.022. And then there's a button that right here that says EE. And sometimes your button might say EXP. But if I use my EE button, that multiplies it times 10 to the, and then I tell it what I want the 10 to the to be, and the answer here is 23. Okay, so when I type this in, I'm typing in 6.022 EE means times 10 to the 23. And that's how I type in this relationship here. So 0.33 times that. And the answer I got, my goodness, that's busy there, is 1.98 726 times 10 to the 23.
Sorry to interrupt again, but I have another question, and it's kind of related to my first one. Where did the 0.33 of silver come from?
It was just given in the question. I just made it up.
Okay. Oh, okay. That's all.
Sam,
I was really like.
Yeah, no, I can't tell you how much I appreciate that you talked to me. You're a role model. I hope that the others are following your lead and thinking about saying something. I would really appreciate it.
Yeah, no doubt. I have a question on significant figures.
Yes. Hi, Charlie.
Hi. I don't understand how you came to the number of significant figures for this answer.
I haven't.
Okay, so it's going to be 4 significant figures?
No, when you multiply and divide, it's the fewer number.
The fewer number, so it's going to be 2.
Yes,
Okay,
exactly.
thank you.
So 1, 2, but I thank you for talking to me. Look to the right. I see that I need to round that up. When I round that up, it's going to end up being 2.0 times 10 to the 23 silver atoms. And then I put a box around it. Questions? Okay, so to get from moles to atoms, I multiply by Avogadro's number. To get from atoms to moles, I divide by the same number. So here it says how many moles, that's what we're solving for. And it's carbon, is 2.5 times 10 to the 24 carbon atoms. So as I'm writing this down, I'm not just putting moles and atoms, I'm also adding whatever the element is, because pretty soon we're going to be going from one element to another, or one thing, species, element or molecule or compound, to another using balanced chemical equations. And then I could say carbon atoms or atoms carbon. Atoms carbon doesn't sound right to me. And I can say moles carbon or carbon moles, which also doesn't sound right to me. But it doesn't matter. The important thing is that I have both ideas, the unit and the species. The unit and the species. And so I happen to say carbon atoms and moles carbon in that order. Carbon atom, carbon before atoms, for example, moles before carbon. Just because I'm used to hearing it that way, it sounds right to me. But it honestly does not matter. Okay, so I'm going to start with my given value, which has 2 sig figs. Usually that limits how many sig figs my answer will have. Oops. And then to get the atoms to cancel, so I'm using this idea, 6.022 times 10 to the 23 pieces in one group. I need the atoms to cancel, so right now I'm dividing by Avogadro's number. Okay, when you do this on your calculator, I'm going to suggest that you use that EE key again, because if you don't, you're going to end up with an answer like 10 to the 47, and that's not the right answer. Sometimes people might want to group this using parentheses, which works, and on some calculators, that's the only way to do it. But practice using your EE or your exponent key. That will save you some grief. If there's anybody that has a calculator that isn't this kind of calculator that wants to talk about how to use yours, if you turn on your video and hold it up to the screen, I can tell you where the key is. Okay, so 2.5 EE24 divide by 6.022 EE23 equals, and I got an answer like this, 4.151444,703. Okay, so this is 2 sig figs, 1, 2. I see it's 5, so I can round to even or round up, but either way I get 4.2. Carbon atoms canceled, and I was left with moles of carbon. That's my answer. Questions? Okay, so to get from the group to the particle, or from the particle to the group, we use Avogadro's number. And depending on which direction we're going, we multiply or divide. But if we want to get to mass, we have to use the periodic table. And so the next problem says, what mass in grams is 0.3 moles of gold? So I need to find gold. And a value on the periodic table. So here's gold. And this value can be interpreted two ways. It could be 196.967 atomic mass units per atom, or 196.967 grams in the whole group. So what mass is what we're solving for? And the given is 0.3 moles. And to go from moles to grams, I'm going to use this number. I'm going to multiply by the molar mass, the mass of a mole, on the periodic table. And the molar mass is 196.967 grams per mole. Only true if we're talking about gold. Gold is like an elephant. It's huge. Two sig figs, 6 sig figs. My answer only has 2. Questions? Okay, so this was going from moles to grams, and we multiplied by the molar mass. On the next one, we're going to go from grams to moles, and now we divide by molar mass. Three sig figs, 5 sig figs, 1, 2, 3. Questions?
Making sense so far.
Okay, good. All righty. So this is a map that we're going to use throughout chemistry, and it's going to get larger. So it wouldn't hurt for you to like draw one of these. But what we're looking at right now is just this idea that I can go from grams to moles. And to do that, I'm going to use the periodic table and a molar mass. And I can go from moles to atoms. And to do that, I'm going to use Avogadro's number, which is the same for any kind of species. And species just means atom, ion, molecule, or formula unit. So any kind of thing, I'm going to use Avogadro's number. And we abbreviate it with an NA, and it's 6.022 times 10 to the 23. We haven't gotten here yet, but pretty soon we're going to learn to get from moles of one thing to moles of another thing. We use a balanced chemical equation. I think that's probably coming up in the next chapter. I'm not sure, I haven't looked ahead yet. And that's the reason that anytime we're talking about grams of something or moles of something, we say grams this, moles this, atoms this. I have to specify. I can't just use the name for the unit, which is grams, moles, and atoms. I have to also specify the species, which in this case is A. Because eventually we're going to be going from one kind of thing to another kind of thing, maybe reactants to products. Okay. So here, I want to figure out how many iron atoms is what I'm solving for. And this many grams. Oh, we lost somebody. And this many grams. So to get from grams to atoms, I have to go through moles. It's a two-step process. Grams to moles, moles to atoms. Grams to moles. I use my periodic table. Moles to atoms. I use Avogadro's number. My grams cancel, my moles cancel. The thing I'm left with are atoms, which is what I want. I have 4 sig figs, 5 sig figs, 4 sig figs. My answer will have 4. Questions? All righty, back the other direction. Oh, nope, not the other direction. This works for compounds too. So here, to get from grams to moles, I needed a molar mass. And we had the molar mass for the element, for atoms, on the periodic table. But if we have a compound, we could just add molar masses together to come up with the molar mass of a compound. It's like building a bike. If I know the mass of the frame and the handlebars, the seat, and 2 tires, I just add them all together, that's the mass of the bike. So that works here for compounds. For water, H2O, we have 2 hydrogens and 1 oxygen. So if I was trying to find how many grams in a mole, I would say 2 mole of hydrogen times the molar mass I find on the periodic table. And 1 mole of oxygen times the molar mass I find on the periodic table.
So for like water, H2O, you'd have 2 for oxygen.
Say it again.
For a compound like water, H2O, you'd have 2 for, H2, 2 hydrogen.
Yep, exactly. This 2 is referring to the number of hydrogens. And that lack of a 1 is referring to the oxygen. Yeah.
Right. I said that backwards first time, but yeah, 2 hydrogen.
But again, I'm just so happy you're talking to me that I don't care. It's all good. Okay, so now I have the mass of the pieces. Let me add those together. 18.02 grams is the mass of 1 mole of water. So I could say it this way. The water's molar mass is 18.02 grams per mole. The units for molar mass are grams per mole. Okay, so how many molecules? I'm solving for pieces. So molecules here is kind of like atoms in the previous problem. And I'm given a mass of a compound. And I can't go straight from grams to molecules. I have to go from grams to moles to pieces. I have to go from grams to moles to pieces. And I use the molar mass here that I find on the periodic table, what we solved for there, and then Avogadro's number to go to how many pieces in a group.
Times 6.022 times 10 to the 23rd.
Yep. Oops.
I had to flip back to my notes.
Which is nice that you have notes. Something occurred to me today. So you're taking this class because you want to take another chemistry class. Like people don't just take Chem A for fun.
Correct.
Probably it's 1A, which means you need to take an entrance test, which means whenever I say this is something you're going to need to memorize for 1A, that means before you take the 1A entrance exam, you probably need to know those things. So just a warning that if you're taking that test, it's coming up soon, and there's some things you're going to have to know, like symbols for elements. And this number, 6.022 times 10 to the 23, is pieces per mole.
Seems pretty important.
Yep. But sometimes if you're taking a class at home and you have access to your notes all the time, it's easy to think, oh, I'll learn that later. Like I'll memorize that later.
I started out that way with this class and very, very rapidly swapped over to notes.
Okay.
I think I'm up to like 15 pages about somewhere. Some of them are really sloppy. But
You're up to what?
like 15 pages of notes about.
Yeah.
I haven't counted it out quite, but it's a lot.
The good news is that it's not wasted. All that effort will pay off in the future. It's an investment.
Yeah.
Okay, so I have 2 sig figs, 4 sig figs, 4 sig figs. My answer is 2. 8.4 times 10 to the 23 water molecules, or molecules of water, however you want to write it. But I have to report both the number and the units. Questions? Okay, Dan, Ryan.
I have just a little one.
Okay.
On your hydrogen atoms, I noticed you wrote 1.01, but on my periodic table it says 1.008. So you're just rounding up a little.
I am. Yeah.
Okay.
You could use 1.008 and you'd have the right answer.
And then round up again. So it doesn't really matter, but then you do that.
Yeah, and we'll get the same answer. Okay, how about the rest of you? Charlie, Arun, Kayla, Ryan, Dan, do you have any questions?
Nope.
Okay, thanks for talking to me. Okay, for atoms or ions in compounds, we can also use this idea. So here the question is, how many lithium ions? Is what we're solving for. And then we're starting with 50 grams of lithium sulfide. So we have grams of a compound. Lithium is a group 1 metal. It loses electrons. It loses 1 electron to become like helium, to have It's element number 3, but if it loses 1 electron, it has 2, like helium has 2, and that's really stable. Sulfide, sulfur is a group 6 nonmetal. Nonmetals gain electrons. Group 6 nonmetals gain 2 electrons. So sulfide has a 2- charge. When they form a compound, it needs to be electrically neutral, which means we're going to need 2 lithiums for every 1 sulfide so that it adds to 0. So the formula for lithium sulfide is 2 lithiums for every 1 sulfide. Okay, so what we want is just a piece within this unit, but first I have to get to this unit. So I'm going to add all these pieces together to get a molar mass, to get from grams of lithium sulfide to moles of lithium sulfide. And then once I get to moles of lithium sulfide, I can get to formula units, which is this idea here, the unit that we use for the formula. And then I can see that so I'm using the 2 within the formula as my final conversion to get from the formula unit to the lithium atoms. So I'm using this 2 here as a conversion to get to lithium atoms. Let me go ahead and do that and we'll see if it makes sense. I don't have the molar mass memorized. I think it's something like 6.97. Does anybody have a periodic table nearby for lithium?
Yes.
Okay.
Which is lithium number? It's in metal. Number 3.
Number 3.
6.941.
Oh, 41. Okay. And then how about for sulfur? It's probably 32.066.
32. Yep, that's correct. 32.066. Okay.
And then there's 2 lithiums, so I'm going to have to multiply that one by 2.
Right.
I'm going to add all those pieces together to get the molar mass for lithium sulfide. Okay, so we've gone from grams to moles. And now to formula units. Yeah, 1 mole is 6.022 times 10 to the 23 formula units of Li2S, lithium sulfide. And every 1 formula unit has 2 lithium ions. Okay, so sig figs, 3 sig figs, 5 sig figs, 4 sig figs. This 2-to-1 ratio here, that's unlimited. That's a counting number. So my answer is going to have 3 sig figs. questions? Okay. So the mole is a chemist's favorite grouping number. You need to memorize it. And then the periodic table is our favorite tool. And one of the really important things it helps us with is giving us molar masses. So that's all I have for today. And as I'm doing this, I'm thinking, wow, this is going really fast. And this is your first, for a lot of you, it could be your first chemistry class. So I've had 2 students, you have a test this week. It's due Sunday by midnight. It's not on this chapter, but it's possible that things are going so fast that things don't have time to settle in our brain and we still have some questions. So I just want to let you know that I have 2 meetings. I'm meeting a student tonight at 7 on Zoom, and I'm meeting another student sometime tomorrow. Oh no, Friday. And I'm happy to do that. So let's say that you have questions, but you didn't want to ask them here, or maybe you weren't sure what they were just yet. If you want to make a list of questions and email me and say, can we set up a Zoom time? If I'm available, and I probably am because I'm home, it's quarantine, we can set up a time, and then I can help you with your particular questions. And it doesn't really matter what the questions are, just anything chemistry or chemistry class related. So I just want to throw that out there, that it is okay to meet one-on-one, and I am happy to spend that time because I want you to be successful. And I understand that not everybody is comfortable talking in front of the group, which is fine. So, okay, that's all I got.
Thanks, Professor Kernet.
You're welcome.
Thank you.
Call me Sue. You're welcome, Dan.
I'm gonna see if I can get some of the homework done right now.
Okay.
Thank you.
See you tomorrow.
Okay, sounds good. How you doing, Arun?
I'm fine.
Good. Do you have any questions?
No.
Okay. Well, good. I'm glad you made it today.
All right.
See you tomorrow?
Sure.
Okay. Bye-bye.